Welcome to Chemistry with Dr. Z. Please subscribe to my channel to get the videos as they are uploaded. This video is we are going to give you a quick revision for the topic 2 for IGCSE and GCSE chemistry, which is the bonding structure and properties of matter. So there are three types of bonding. The first one is the ionic bonding. So ions are formed when electrons are transferred. So when metals lose electrons, they will form positively charged ions, and nonmetals, when they gain electrons, they form negatively charged ions. All the metals or nonmetals, all the elements will try to gain or lose electrons in order to reach the a full or to get to a full outer shell of electron, which is the more stable configuration for the atoms, so they tend to lose or gain electrons to form ions. The group 1 elements will lose 1 electron, group 2 element 2 electrons, group 6 elements will gain 2 electrons, and group 7 will gain 1 electron. Ionic bonding comes from when metal and non-metal react together. The metal will tend to lose electrons to give positively charged ion, while non-metals will gain that electron to give negatively charged ion. The positive and negative or the oppositely charged ions will have now a strong electrostatic interaction to interact with each other and to form the ionic bonding. To represent the ionic bonding, we can use the dot and cross diagram. So something like sodium and chloride, you have the electron on the sodium and the outer shell of sodium as a cross and the electrons on the chloride as dots, and you can represent the move of the electrons from sodium to chloride to form positively charged ions of sodium and negatively charged ion of chloride, and then there is an electrostatic interaction between both of them. Don't forget to add the charge on both ions to represent the interaction between the different atoms, between the different ions. You can do the same for any type of atoms. Just make sure that you represent the electrons with the dot and cross for different atoms or different ions. The ionic compounds, these are the compounds which have ionic bonding. They have a regular lattice structure called the giant ionic lattice, something like sodium chloride as we can see here. There are sodium ions and chloride ions with electrostatic interaction between them to form the giant ionic structure. The ions form a closely packed regular lattice arrangement, and there are very strong electrostatic forces of attraction between oppositely charged ions in all direction in the lattice. So the properties of the ionic compound, first of all, they're gonna have very high melting point. This is because as a solid, the ions are very close to each other, closely packed, and there's a very strong electrostatic interaction between the ions. When they are solid, they cannot conduct electricity because the ions are fixed in their place. They cannot move to carry the electric current. However, when molten, the ion now can move, so they can conduct electricity. Also, if you dissolve the ionic structure or the ionic compound in water, then now you're gonna have separate ions, positively and negatively charged ions, and then they can also conduct electricity. The second type of bond is the covalent bonding. So covalent bonds is formed between a non-metal ion. It comes from sharing of electrons. So covalent bonding is the share of electrons. The electrostatic interaction between the positively charged nuclei of both atoms that make the bond and the shared electron will make the covalent bonding. So covalent bonding themselves are a strong bond. The covalent bond is a share of one pair of electrons between two atoms. These two atoms could be similar type of atoms, so making molecules from the same element, or it could be between different elements, non-metallic elements, to form compounds. So how can we draw the covalent bonding? The first one is via the use of the dot and cross diagram in the same way as we did with the ionic bonding. However, now the electrons does not move from a metal to a non-metal, but there is a share of electrons. You're gonna use the dot and cross to represent the electrons that come from two different atoms, even if they are the same type of atom or if they are the same element. And then in between them, you're going to represent the shared pair of electrons. Some atoms can share more than one pair of electrons to make more than one covalent bond, like oxygen, where there are two pairs of electrons. In nitrogen, there are three different pairs of electrons. So nitrogen, two atoms of nitrogen will form three bonds in between the two atoms. We can also show the dot and cross diagram for sharing electrons between different elements in a compound, like water, for example. So water has two hydrogens and oxygen, and the oxygens share one electron with a different hydrogen, and the electron of the hydrogen is represented by the cross, and the electron from the oxygen is the dot. Each one of these is a pair of electrons which represents one covalent bonding. We can also draw the covalent bonding using the displayed formula. In the displayed formula, covalent bonding are drawn as lines between atoms. Like here in ammonia, we drew the bond between the nitrogen and hydrogen as a line. If there is two bonds together, you can draw it as two lines, for example, between two oxygens. So two lines will represent the double bond or the two covalent bonds between the two oxygens. It's very useful to show how atoms are connected in large molecules. So it's more useful in larger molecule than the smaller one. The third way is the 3D model like this one, and it can show the atoms, the covalent bonds, and their arrangement in space next to each other as well. So the properties of the covalent bonding of covalent compounds. So we have what is called the simple covalent compound. Simple covalent compounds are these compounds which have limited number of atoms. So there are the smaller molecules like these ones we can see here, like the oxygen and carbon dioxide. The first thing is that they do not conduct electricity. The main reason is because there are no ions, or there is no electrons or ions that can carry the electric current, so they do not conduct electricity. And then let's have a look at the different bonding between them. So there is a strong covalent bonding between the atoms of the same molecule. However, between the different molecules, there will be very weak intermolecular forces of attraction. So it's easy to overcome this intermolecular force of attraction because it's quite weak. This is why simple covalent compounds have low melting point, because we can break these weak intermolecular forces. Polymers is another example of simple molecular structure. However, they don't have a limited small number of, they are unlike the smaller molecules, they are quite big. They are formed of repeated units of the same structure. For example, the polyethylene here is one of the polymers. This is the repeated units. You can keep drawing the exact same unit on both sides. We can normally draw the polymers by drawing only one of the repeated units and put that between brackets and put the letter N to represent the number of repeated units. As property, so first of all, they're going to have melting point, which is going to be higher than the smaller molecules, but they are still lower than the ionic structure. The main reason why their melting point is higher, because they have bigger structure, and because they have bigger structure, the electrostatic interaction, the intermolecular forces between the polymers or between the molecules will be higher, so they will need more energy to break this intermolecular forces. So they will have melting point higher than the small molecules. Then we have the giant covalent structure. Giant covalent structure are these structures which only have covalent bonding and they usually have high melting points. So let's have some example, have a look at some examples. So silicon dioxide is the sand. So sand grain is formed of silicon dioxide. Silicon dioxide is a giant covalent structure formed of covalent bonding between silicon atoms and oxygen atoms. There are no other type of bonding other than these covalent bonding, so this is why they have very high melting point. Another example is graphite, and graphite is formed of carbon, and they are formed of layers of carbon structure. Each carbon in each layer will have three bonds with three different carbon atoms to form hexagonal structures, and these layers will have a weak bond between them in addition to the strong bonds or covalent bond within the layers. And then we have diamond. Diamond is one of the giant covalent structure. Also diamond has very high melting point. It's formed only of carbon atoms with a covalent bonding. Moving on to talk about the allotropes of carbon. So allotropes are different structure forms of the same element, meaning that these structures will only have one element, but they are linked together in a different way. So the first type is the diamond. So diamond is one of the giant covalent structure. It's formed of only carbon atoms. So each carbon atom is linked with four bonds with four other carbon atoms. Each carbon atom has four electrons in its outer shell. So all these four electrons are shared with four other carbon atoms to make the diamond. So the properties of diamond, they do not conduct electricity because they don't have any delocalized electrons or ions to conduct the electric current. They have very high melting point because the covalent bonding is very strong, and it's very difficult to break the covalent bonding between the carbon atoms, and they are very hard as well. The second allotrope is graphite. So graphite is made out of layers of hexagonal structures made only out of carbon. Each layer we have a different carbon atom. Each carbon atom form three covalent bonding with three different carbons. And then because the carbon has four electrons in its outer shell, there is one electron that is delocalized or can move freely. So graphite have high melting point because of the strong covalent bonding between the carbon atoms in the layer. However, the layers have weak bonds between them, so the bonds between the layers can easily be broken. So they can slide over each other or past each other the layers, and then this is why graphite can be used as a lubricant. However, they can also conduct electricity because of the delocalized electrons. So they have one free electron in each carbon atom that does not take part in covalent bonding. It's not shared, and so they are delocalized. They can move freely, so graphite can conduct electricity. Graphene is one layer of graphite. So basically, it has the same properties as graphene as graphite because it's simply the same structure as graphite, but it's only one layer, not several layers. They have very high melting points because of the very strong covalent bonding. They are very light and thin, and they very thin and light because they are only one layer of the carbon atoms, and they also conduct electricity in the same way as graphite because they have delocalized electron, as each carbon atom is only bonded with three other atoms, leaving one electron free to move. Fullerene is not one of the giant structure. Fullerene is it's not a giant structure. However, it's one of the allotropes of carbon. One of the examples of fullerene is C60 fullerene, which means this structure has only 60 carbon atoms. The fullerene will form hollow balls or hollow tubes. Each carbon atom will form three bonds with three other carbon atoms. So they also have one free electron to move from each carbon atom so they can conduct electricity. They still have high melting points as well because it's difficult to break the covalent bonding between the atoms. And they have this hollow structure. The carbons are arranged in polygonal forms, so like pentagon, hexagon, or heptagon. Fullerene, because of their unique structure, they have unique properties and uses. So they can be used in drug delivery because the drugs can be entrapped inside the hollow balls and they can be used to deliver the drug into the site of action. They also can be used in industrial catalyst. This is because the they have a very high surface area because they are quite small in size. They have very high surface area, and then because they have high surface area, they can actually the um, uh, the catalyst can be attached to the surface of the fullerene, and they can be used in industrial catalyst, providing a high surface area for catalysis. They also used as good lubricants. Fullerene nanotubes is another structure of the fullerenes because we said fullerenes can be also, they also form tubes or hollow tubes. The properties of these that they can conduct electricity and thermal energy. This is because of the free electron that can move. They have delocalized electrons and they have a very high tensile strengths, meaning they can be stretched without being broken. So they are very light and they can conduct electricity. So they can be used in electronics. They can provide strings without being broken and they can also conduct the electricity. The third type of bonds is the metallic bonding. So metallic bonding is a type of bond that you can find in metals and in alloys. The bonding comes from an electrostatic interaction between positive metal ions and delocalized electrons. So each ion, each element of or each one atom of the metal will lose an electron or will have a delocalized electron from their outer shell, and there will be a strong electrostatic interaction between these delocalized electrons and the positive metal ions. That will keep the metal in place, and this is why metals will have a giant structure in the same way as the ionic compounds. Because of the delocalized electrons and because of the strong electrostatic interaction, metals have very unique properties as well. So we can now see that most metals are solid at room temperature because of the strong electrostatic interaction between the positively charged ions and the delocalized electrons. They can conduct heat and electricity because of the delocalized electrons, which can carry the electric and heat waves. Most metals are malleable and they can be hammered into shapes because when they are arranged and the layers of the metal can easily slide past each other, as we can see here, so they can easily be hammered into shape. Alloys is another type of structure that we can see the metallic bonding. Alloys are not formed only of one metal, but it's formed of more than one element. One of these must be a metal. So it can be either two or more metals, or it can be metal with a non-metal. So pure elements themselves are too soft, and they are, when they are mixed with other elements, they make the alloys. The alloys are more useful than metal because they can make the metal, or the alloy is harder than the metal itself. The main reason for that is because when you add another element in the structure of the metal, you're gonna find that because they have different sizes, they can distort the arrangement of the metal ions. So when they distort this, then the layers of the metals cannot slide past each other easily. So pure metals are easily malleable and they are soft. However, the alloys are more brittle, and they are hard. Nanoparticles, we can categorize the particles based on their diameter as coarse particle, fine particles, and nanoparticle. We are going to talk about the nanoparticles, which have particle diameter of 1 to 100 nanometers. So nanoparticles have a very unique property that their surface area to volume ratio is quite high because they have very small size, and when they have very small size, then the ratio between the surface area, they're going to have very high surface area, and the ratio between their surface area to the volume will be very high, and this affects the properties of the material or of the nanoparticles. So, because of their high surface area to volume ratio, they have unique uses. So, first of all, or many useful uses. So, the first one is that they can be used to make new catalysts. The main reason for that is that they can provide a very big surface area for catalysis, which can fasten the process and allow the use of a smaller quantities of the catalyst. Second of all, they can be used in delivering drugs right into the cell where they are needed. The main reason for that is because they have very small particle size, then they can easily be absorbed or pass through the membrane, so they can allow the drug to reach its target, its site of action. They can also be used in electric circuits for computer chips, and they can conduct. Some of them can conduct electricity, and they can be used in electric circuits. Silver nanoparticles have antibacterial properties, so they can be used in surgical masks and wound dressing, and they can also be added to deodorant. Nanoparticles as well have been lately used a lot in cosmetics and in sunscreens. So, but however, there are with these very useful uses of the nanoparticle, there are some controversy around its use. So the main reason for that is the use of the nanoparticle is still in early stages. This is quite a new area of research, and a lot of nanoparticles have been used. However, the long-term effect of the use of these nanoparticles is not well known or not well documented. This is why all products that contain nanoparticles should be clearly labeled so the consumer can decide whether or not they would use this product. And some of the examples of the unknown effect of the nanoparticles is their use in sun creams because they have better protection against the UV rays. But it's not known whether these nanoparticles are absorbed through the skin and have any effect on your body or not. So this is the long-term effect as well of its use and whether it can be absorbed and have damaging effect or not. The final thing we're going to talk about is the state of matter. There are three different states of matter, which are solid, liquid, and gases. The state of any material at a certain temperature will depend on how strong the forces of attraction between the particles at that particular temperature, which will mostly depend on the material itself, the nature of the material. So there is something called our model called the particle theory, and the particle theory explains how the particles in a material will behave in all different three states of matter by considering each particle as a small solid and elastic sphere. So let's have a look at the solid. So the solid will have strong forces of attraction between all the particles. These strong forces of attraction will allow the particles of the solid only to vibrate in place and they cannot move. So particles don't move past each other, they do not move from their position. This is why they have definite shape and volume and they do not flow. They only vibrate in their position, so they have fixed position. When we look at the liquids and then using the particle theory model, you're going to find that there are weak forces of attraction between the particles of the liquid, so the liquid particles can move more freely. However, they still stick to each other. They have a definite volume, however, they don't have a definite shape because they can move freely past each other. The gases, then, they have very weak forces of attraction in between them. They are free to move and they are far apart. They don't have a definite volume or a definite shape. The particles are constantly moving with random motion. Finally, let's have a look at the change of the state of matter between solid, liquid, and gas and use the particle theory to explain that change. So first of all, let's start with the change from solid into liquid, which is the melting. So when solids are heated, the particles will gain energy and the particles will start to move faster. And then at melting point, the particle will have enough energy to break free from their position. So they will melt and change from solids into liquid. And then the liquids, when they change into gases, as we know this as boiling, the liquid will be heated and the particles will gain energy. The particles will move faster. They will have enough energy to break from the bonds completely. And at boiling point, the particle will have enough energy to break their intermolecular forces completely. They will boil and the liquid will become a gas. And then gas can change into liquid with condensation, or it can condense into liquid. So gases will be cooled, and as they get cooled, the particles will lose energy and they will move slower. The forces between the particles will be regained, and then at the boiling points as well, the particles will have enough intermolecular forces in between them, and then they will condense from gas into liquid. And then liquids, when they are cooled, the particles will lose their energy. The particle will move slower, and then at the boiling and the melting point, the particles will have enough intermolecular forces between them. They cannot overcome the forces of attraction between them, and they can only now vibrate, so they can change their state from liquid into solid. This is called freezing. At the end of this, don't forget the state symbol in your chemical reaction. We need to state the state symbol in any equation. So we have four state symbols: S for solid, L for liquid, G for gas, and AQ for aqueous. And aqueous here means that your compound or your element, your substance in general, is dissolved in water.